oops, not 1127, it's 1175, wasn't it? The singly charged mass will be 4698. If I take away 3157.53, so the mass of the glycon on this one should be 1540.5. $1540.5. Makes all the difference when I put the decimal places. Okay, so HNAC2, hex 7. Then we've got a 1215. And again, we've got a big 1121, so we've got another version of the same peptide. $1215.79 times 4, take away 1705. I think it should be 1702. Right. $1215.79. Multiplied by 4. Take away 3. That's the singly mass. Okay. $1702. So that peak is HNAC2, hex 8. So our high manage is getting higher. And then the last one that was selected for fragmentation is this 1264. And this 1264, do we think this is the same peptide? No. No, this looks completely different. So we don't have the 1121, and we've got a fairly big 274 peak, which suggests this contains a cyanic acid. So this is another glycopeptide, and it's not related to what we've got. So the summary of all of that, is this. So the two peaks at the far end were different peptides, and then all of these other peaks are different glycan structures of the same peptide, all co-eluting. So I've got one last little test for us. Well, in fact, I've got two related tests. So we've just been looking at some N-linked data, so let's have a look at some O-linked data. So this is the CRD spectrum of an O-linked glycopeptide. As you remember, for O-linked glycosylation, it's labile, so the sugar falls off, and in CID we're unable to identify the site of modification. So based on the mass, we know this has a single hexac attached, but we don't know which one of the 5 serines it could be attached to. But hopefully in ETD we can identify the site. So this is the ETD spectrum. So the question is, okay, so I've split the mass range in half here. So it starts here, and we're going up to 1,000, and then the bottom half we're going from 1,000 to up to 2,000, because we've got lots of peaks in here, and otherwise it'd be very difficult to see it. And so this is the ETD spectrum. So in here, the modification should be staying attached to the peptide. So the question is, from these fragments, can we work out which of those serines the modification is on? So for that, we're going to need this program MS product we were just using. What's the sequence for our peptide? ETD. So this is a table that's going to give us the masses of fragments we would expect if the peptide was unmodified. So I haven't put the modification anywhere at the moment. So let's see if we see any of these peaks to start with. Too small, isn't it? Let's see. Do we have a 419 anywhere? We do. We have a 419 here. So that 419 peak must correspond to a C5 ion with no sugar attached. So therefore, based on that peak alone, we can say the modification is not on the first serine and it's not on the second serine in sequence, because we're seeing that unmodified. Then next we've got a 518. So that's the next residue along. So that's SGV, ASV. And that's also not modified. 647. 647. What do we have after that? Let's see. Our next expected C ion would be a 734. Do we have a 734? Yes. 821. Yes. It's very small, but it's there. 908. No. No 908. So we're not seeing a 908. What if we put the hexac on that 908? What mass would we expect then? Oops. Which serine was that? So that's the third of the 3 serines. So now we'd be expecting a 1111. There it is. So we've got the mass shift on that third serine. So therefore, the modification site must be on this third serine here. Let's see if we see any other fragment ions that confirm that. So the next peak we would expect would be an 1168. There it is. Smaller. Is that legible? It's very small, isn't it? $1168, $1297. There's 1297, 1368, 1368, 1515, 1515. So we're seeing all of these ions are now shifted by having the mass of that hexagon on there. So we've been able to identify the site of modification. So that's no link with just a single hexagon.
Sorry,
Yep.
the peaks between 821 and 1168.
Mm-hmm.
What are?
Let's see. So the ions we were looking at there were all these C ions. So one's getting bigger from the N-terminus. Let's see what masses the Z ions should be. So I need a bigger screen. That's what I need. So for the Z ions, can I get this on the page? Resize. So the 828, we don't see 828 or 1118. So what are these peaks? So I can't tell you what a lot of them are. So this 905 here is that's probably the second a later isotope. It's probably the first isotope is probably this. So it's probably a doubly charged C ion. So it's a really long stretch of the C from the N-terminus that has two charges attached. So we were looking at everything there with a single charge, but our precursor had 4 charges on it, and so it's quite easy to get doubly charged fragment ions from it. And so that's what some of those peaks are. I was expecting some of them to match Z ions. But yeah, my screen is not big enough to get things on. So is there you might get an 804, 839, 889, any of those in there? So yeah, that 840 is probably 839. So I don't know. So if you zoom in on these peaks, they actually have isotopes. It's not just a single peak. I was trying to gloss over this. So the 99% of carbon is carbon 12, but 1% is carbon 13. So I mean, obviously 1% doesn't sound very much, but if you've got a molecule that contains 100 carbons, then all of a sudden that second isotope peak is going to be as big as the first isotope. And what's happening here probably is, I mean, the second isotope, the software has labelled the second isotope here at 840.4, when the first isotope should be 839.9. So this is a doubly charged peak, so therefore the isotopes are going to appear half an m over z unit apart, because we have to multiply everything by 2 to get the singly charged mass. And so what some of these peaks are doubly charged fragment ions.
So I have another question. You mentioned that some of the peaks are very small. Does that tell you anything about the protein? It's just because of the efficiency of fragmentation, or?
No, it doesn't tell you a great deal. So I mean, peptides are not, amino acids are not homogeneous, and so some, cleavage N-terminal, C-terminal to certain amino acids is easier than others, and so the intensity is in some way related to the amino acid sequence, but it's very difficult to predict. So certain cleavages are very heavily favoured. For example, in collision-induced dissociation, cleavage N-terminal to a proline is always very big. But this peptide doesn't have a proline in, so that's not an example here. But it's very difficult from the intensity to say anything particularly useful. I don't know what else. But, yeah. So we've identified the modification site in this one. I put another one in. Do we want to go through this last one? It's going to be essentially the same as the last one, but it's a different peptide. So here's the CID spectrum of this particular peptide. It's got a bigger structure on now. It's got a hexnac hex mu AC. So we can see. Yeah, we've got the big 274, which is confirming the fact it's got the sialic acid on there, and we've even got the 204 for the hexnac and the 366 for the hexnac hex. So we have all the fragment lines for that, and this is presumably the intact peptide with the sugar falling off. So this is probably doubly charged. And so here is the corresponding ETD spectrum, and we're going to go through again and see if we can work out where this modification is attached. So the precursor was a 1035 3+. So that's actually the precursor ion, and these are the fragments. So this is going to tell us the fragments. I haven't put the modification anywhere. So this is going to tell us the fragments you would expect if it was unmodified. Let's see if we can find any of these peaks on the list. Let's see. I'm going to cheat and get it to label fewer peaks, just so I can get things on the screen. Okay, that's going to be a lot easier to work with. So I'm just getting it to list the C and Z ions, which are the things that we're most likely going to see. So we've got a 611 here, which corresponds to a C6 ion. So we know the modification isn't on AAPPQE. That's not really telling us very much because the modification couldn't be anywhere on there. Let's see if we see any other bigger ions. Do we see a 726? We do. An 813. It hasn't labelled it. I wonder whether that's 813 or not. We see a 941 though. The next one will be 941. So I bet you that's 813 and the software hasn't labelled it. So we've got a 941. Do we have a 1012? We don't. Do we have an 1113? We don't. It's 1242. So we're not seeing any of these peaks now. So the biggest one we've seen there is 941. So we know that the modification is not on this part of the peptide. So it's not on this serine. But we've still got lots of other residues it could potentially be on. So let's look at some fragments from the opposite end, some C ions. So 622, do we have 622? We do. 735, we have a 735. 792, that's probably 792. It's labelling the wrong thing, probably. 893 is 893. 1008, 1008. So we know that the modification is not anywhere in here. So we're now left, it's on one of these two threonines. Can we determine which one it is? So when we don't have any singly charged peaks that are going to correspond to this, it's probably going to be a doubly charged peak. So do we see a 603? Not really. 668? No. 718? No. So you don't have any ions on that end. See if we can work out what some of these peaks are. So it's going to be on one of these two threonines. So let's try putting a modification on one of them and see if we can find a fragment ion that has the sugar attached. So the modification was hex, NAC, hex, I think SA for sialic acid. Okay, so we have a 1769 here. We have a 1769 which corresponds to this C ion with the hex NAC, with the whole sugar structure attached. So that ion is telling us that it's on this first threonine and not on the second threonine.
But if we try in the second?
So if instead we had the modification on the second one, and these would be the ions you'd expect. So obviously there's no longer a 1769 because this is, modification is not there. So we can't explain any of these high mass peaks. I think if I'll put it back on the other residue again. Oops. I can't copy and paste. What do they do? I'm mad. So we saw this 1769, but there's also, the next fragment would be in 1898. So we have another peak that's explained as well. So we've got there eventually. So you can see this isn't very easy stuff to do. The software can actually do a lot of this for you. The database search engine, you saw in the examples yesterday, it was putting the modification on a specific site. So it is going through and looking for these ions and saying, based on this, I can say that the modification is on this residue and not on another. And so if you use software like Protein Prospect, it's going to give you the site localization information if it's in there. So you do get situations when you don't see fragments allow you to identify the exact site. So if you have two serines that are right next door to each other, if you don't see the fragment in between those two, then you may not be able to identify the site. And so the software can indicate that it's ambiguous, and so it will say it's one of these two. But hopefully most of the time you can identify the site. That's it. You've survived.
On the first software, I think it. On using the first software, I think instead of you have to select the number of sugars you imagine to complete or account for the mass of the glycan.
Yeah.
If the software can propose all the structures you can have.
Yes. So there is software where you can give it a database of sugar structures you can consider, and then it would match it based on that. So also, we've done this search with a mass modification. If instead we had said consider these 20 different sugar structures, then the software would come back and would have put hexnat 2, hex 5 when it saw 1216. It's a function of the way we're doing this initial search to try and be unbiased and say we want to consider any type of structure, and then we're then going to explain it afterwards. And so also you can also, I have an Excel table on my computer that I just pull up and it has masses in one column and compositions in the other. And so I have my own cheat sheet that I can go through and say, whenever I see this mass, what composition could it correspond to? So, we were doing it from first principles here to try and explain how we're actually getting there. But you can have the answers in the back of the book and look them up.
Thank you.
In the case of we have that results, we can build a model, dynamic model to all of that results.
I don't understand the question. So.
Yeah. If we have all that results.
Okay. Yeah.
And then we can build a model that with all that results.
So you want a summary of all the identifications that we got in the whole? Yes. So can I find an example? Do I have any good examples? See if this works. See if I can. Is that going to work? Do I have access? Okay, that's not going to work. So, I must have a good example. Oh, I'm clicking. I'm trying to connect to the actual full results from that particular data set, but it's being tricky. The other thing I could do is find the paper. This will give me the answer. Okay, so this is actually the summary from this whole data set. So in this particular study, we identified about 2,500 glycopeptides. And so this is the sort of output that the search engine is going to give. And so we've got a session number for the protein name here, and then we've got a peptide with a sugar composition, and which sample it was in, and information about the protein. So the top match here is sulfated glycoprotein. And so this report goes down. There's 100 on that page, and then there's another 8 pages of results here. So we've got a very big summary table here that's listed all of the glycopeptides we've identified from all the different proteins. So that's the first protein. Second protein, LRP1, is pro-low density lipoprotein receptor related protein 1. Bit of a mouthful. So somewhere in this report is going to be the example we were just going through. It's going to be tricky to find. Oh, actually, it isn't tricky to find. Tell it what we're looking for. So, see if we can find this peptide. Probably enough. Peptides. I'm going to try and look for this peptide. Sorry. But the answer to your question is you'll get, from the software, you're going to get this very big summary report. And the peptides will be listed by protein, and you can sort it and say, I want it listed by start residue or something like that. So all of the different versions of that peptide will be grouped together in a report. And so you'll have a list where one particular N-glycosylation site, all the different versions are together, and then below that you may have other glycosylation sites in the same protein in another group, and then you'll go on to the next protein.
Right. Talking about the N-glycan proposed by the software, the number calculated or estimated must be really similar to the calculated in the spectrum. When we are trying to guess the glycan, we get a number and then compare it with the number obtained by the software. And I saw that you try to get the most identical number to the...
Yeah.
Yes, it should be...
Yes, so, I was being very lazy with the decimal points on there. So depending on the mass spectrometer, this will determine how accurately you're measuring those things. So all of the masses we've got here are actually correct to within something like 10 parts per million. So what's that in real terms? If something of a mass of 1,000 is going to be correct, 1,000 plus or minus 0.01 Daltons. So we're measuring them very accurately. So it should be correct to 2 decimal places.
And another question, but this is about the script that you use when you try to get the fragmentation of the peptide. And do you put X, NAC, blah, blah, blah? How do you know what grinder?
How did I identify the peptide to start with?
Yeah.
Okay, so I used the software. I gave it all of the spectra and told it to do this database search, allowing for these mass modifications. So my talk. So I gave it the peak lists, and I told it to search sequences in a particular database. So in the SwissRot database, which is a protein database, I told it only consider proteins that are rodent. This came from mouse. I could have told it only consider mouse sequences. I told it that this is a peptide that's been created by digestion of trypsin, and so on the basis of that, it can go through and calculate all the potential sequences of every single tryptic peptide from any rodent entry in this SwissRot database. And then I told it to allow that there could be a modification on either an asparagine, a serine, or a threonine that could have a big mass. And so on the basis of this search, it came back with a result, something like this, where it's identified a peptide and a modification mass.
Okay.
And so the starting point was basically, we were starting from one of these results. It wasn't this peptide, it was a different peptide, but...
I not was clear, very clear. I refer to the nomenclature that you use in the software.
Oh, okay. So because the mass spectrometry is only, can't tell the difference between a GalNAc and a GlucNAc, or a galactose and a glucose. It's only saying that it's a pentose or a hexose or whatever. So we're calling them hex and hexNAc. Is there a standard nomenclature for what these are called? No. I think most people would use hexnat and they'd use hex. It gets a little complicated when you go to the sialic acids, because a lot of people just put SA sialic acid, which is fine if you're working in humans because they only have one major type of sialic acid. But if you've got samples like this where it's mouse data where they have neuraminic acid and N-glycol on neuraminic acid as well, then we probably should be using different names. So at the moment, in the software, SA is N-acetyl neuraminic acid, and if you want N-glycol neuraminic acid, you put SA-ox for an oxidized, because the mass difference is an oxygen.
¿Te lo pasas?
Well, hopefully I didn't confuse you too much.
No, actually, it's a very nice software.
A general approach to identify glycopeptides can be to do a CID fermentation first to know what peptides have sugars, and then to do a second ETD
Yes.
fermentation.
Yes. So we like to have both the CID and the ETD data because they both give us useful information. For identifying the peptide, the ETD is most useful. But having identified the peptide, as you saw in what we went through today, you can identify all the different sugar compositions from the CID data. And you can sometimes get structural information. So, and as I said yesterday, you can tell the software to acquire CID data, and only if you see these sugar ions, then acquire the ETD data. So you don't have to acquire CID and ETD on every precursor. Although, if after your enrichment 80 to 90% of the things are glycopeptides, then you might as well acquire both. It doesn't save you much time.
More questions?
Yep.
Which kind of organization is not
Or used to study glycopeptides is MALDI or electrospray ionization?
So it's most data is electrospray. So the big advantage of electrospray is that you can interface it with chromatography. So you can have a complex mixture and separate the things, and as they elute, you can analyze them. If you're doing moldy, your sample is a solid, and so what you'd have to do is you would have to fractionate your sample, collect the fractions, and then spot each fraction onto each side. So most people are not patient enough to do that, or you can get robots to do that, but it's much slower throughput. So in these examples, we're requiring 5,000 MSMS spectra in a 1 hour run. If you were doing moldy, you would not be able to acquire data that fast. Okay, you're free to go.
Thank you very much, Robert. Entonces, pues nos vemos a las 11, tienen media hora para que las cenas en la sesión.
Okay, demonstration. So, the software is called Trophy Wizard, and there are two main programs in there. One is the so you need to give it a file you want to convert. .raw. .mdf.
I can
Okay. Yep. We're using the software. Yes. So, you go to the home page. There is video tutorials. So these are all focused on, there isn't one that's focused on glycopeptide analysis, but it's mainly focused on peptide analysis in general. So trying to do something very simple. So if you can use the exact quote I used here to search the data. So I mean the difference is so if you remember